Alright guys, so 25 milliliters is essentially going to work out pretty much the exact same way as our 10 milliliters. The only thing that's going to change is the amount of base that we're adding, and so of course that's going to change up the numbers. But the scenario is going to work out exactly the same. We're going to do a stoichiometry part, and then we're going to recalculate our molarities. We're going to do an ice table then, and then we're going to plug that into our Ka value to get our X and then be able to calculate our pH. Now, why is it going to work out exactly the same? Well, as you'll see at this point is that it's going to work the same for everything up until we get to the equivalence point, because until we get to the equivalence point, we're still talking about a Ka value. We've still got an acidic situation, and so we're still working from that equation that we had back at the very beginning. So let's plug in our numbers here and see what our 25 milliliter looks like. So of course we've still got the same initial value for moles here. Whoops, I'm just going to throw random decimal places apparently. So 0.005 moles of the acetic acid. And then in this case, though, we're going to have 0.0025 moles of the hydroxide. Okay, still 0 over here and all that stuff. And then, of course, since this is still bigger than this, we're going to neutralize some of the acetic acid, but not all of it, with the hydroxide. So we're going to end up with 0 hydroxide. We're going to end up with 0.0025 of the acetic acid, and we're also going to end up with 0.0025 of the actual acetate ion, right? Now, why is that? Well, because 1-to-1 ratio again, so we've got that. And so now it's an issue of calculating our new molarities. So now we've got 25 plus the original 50 for 75 milliliters is our volume. So we're going to plug both of those guys in. Then we're going to punch those into the calculator. Now, we punch both of those into the calculator. What we're going to get in each case, because they're the same calculation, right, is 0.0333, okay, molarity for both of them. Whoops, 333, okay. And then that means, next step, let's get down here and do our ice table again. Okay, so now we've got some initial concentrations. We're going to look for some equilibrium concentrations, and so we're going to work it from here. I'm going to take the lazy man's way out here. I'm just going to write the generics. But remember that this A- is the C2H3O2. Okay, so we have no hydrogen at the beginning, and we've got 0.0333 of both the acid and the acetate, right? So both of them were 0.0333. As sort of standard at this point is we're going to lose the acid and gain our conjugate base and our H+. And so that's going to leave us with these guys. Okay, don't worry guys, one of these days, someday, like I'm 150 something videos in, at some point I'm going to learn how to write on this. It's harder than you think. Remember, I'm looking at the screen while I'm writing and not looking at it. So, and let's be honest, I have terrible handwriting anyway. So that gives us all that. And again, since we're using that same Ka value that we've been using, okay, 1.8 times 10 to the negative fifth, it's pretty safe assumption for us to say, hey, we're going to get rid of those x's. They're relatively small compared to their numbers. And so that will ease up our math a little bit. 0.0333. In fact, in this case, your math is even easier because since these are both the same concentrations and we got rid of the x on both of them, we just cancel them out. And so x actually equals our Ka value. X equals 1.8 times 10 negative fifth. And so that means that in this case, when we plug that into our pH value, we're going to get, I think, 4.74. Okay? Now, jump back to our graph. Okay, and we'll plot that. So 4.74, again, we're a little bit above where we were before, but probably not a massive amount. So let's go ahead and put that guy, say, right here. And you can already sort of see the slope of the graph, okay, arcing upward a little bit. And then you can tell that what's going to happen here at some point is we're going to go up like that. Okay? So We're deep in, and now, and what happened there is we're kind of at the halfway point as far as the acidic part. So we'll do one more. Now, if you left this out, I don't know that anybody would really massively criticize you, but I think it's safe, usually if you do maybe 2 or 3 on each side of the equivalence point, and probably want to do more on the beginning side so you can really see the shape of that curve as you're going through there. Okay, so same scenario, just different numbers. So now that I'm up to 0.40 milliliters, I've got 0.004 hydroxide. We've got our 0.005 acetic acid still. This is going to end up being 0. This is going to end up being 0.001. And don't forget your acetate. Okay? So don't forget, what happens on the other side of the equation. Now we're going to go back in and divide by our new volume. And our new volume, of course, is 90 milliliters, 50 plus the 40. The original 50, right? So I don't know what's going on here. So 0.090, that's the coolest decimal point ever. It's actually above where the numbers are. Okay, and so we're going to crank this math out real quick. Or if you're lucky, you've already calculated the math. And so that gives us 0.0444. And that is awful. Okay, so 0.0444 and then 0.0111 over here. And again, we're going to set up our same ice table that we've been setting up the whole time, right? So nothing really has changed here other than the numbers. Hydrogen, the conjugate base, and then HA. We've still got 0 of this. We now have 0.0444. By the way, if you don't like the way these decimals are looking, then that's why we should use millimoles instead. That would make life a lot easier. Okay, so we're going to be adding hydrogen. We're going to be adding acetate. We're going to be losing our acid. And so again, same scenario that we've been working for on the past few steps. Okay, and so I'm just going to run through those real quick and show you what we get. Okay, so we go back in and we plug that in with our Ka value. Now this is, we're sort of getting to the last point where we're going to be using this Ka value, and we'll see why here in a second. But we've had a good run of working several steps using the same basic setup. And so what that allows us to do then is to calculate everything on the left side of the equivalence point. Alright, so we solve that and we're going to get a value of x equals 4.5 times 10 to the negative 6th. That is going to give us a pH value of 5.35. Okay, so now again, we hop back to our graph and we say, okay, so again, I'm just a tad bit higher, and I'm quite a bit higher on the volume. But, okay, so we're getting in the 5-ish range, so maybe around here. And so again, you can tell that this is kind of the point where your graph is going to start to inch up a little bit, right, as we approach the equivalence point. Okay? And chances are that our next point is actually going to be the equivalence point. Okay? So how do I know that? How do I know that it's going to be the equivalence point? Well, when I plug in my initial value, so we're at 50 milliliters, and remember we said that we knew that we initially had 0.005, right? And so whenever I get 0.005 of this, then they equal out, right? That's my equivalence point. That's when the acid and the base cancel each other out, okay? So when does that happen? That happens here, and that's at 50 milliliters. So that automatically tells you on the graph, you know that the vertical part there, that equivalence point that you're looking for that's so important, that is going to happen at 50 milliliters for us in this case, okay? And so we're going to zero this stuff out, okay? So we don't have either our acid or hydroxide at the end. Instead, after we've done this reaction, what we have left is 0.005 of the acetate. Now, that matters a lot because at this point, I don't have an acid in the solution. What I have is a really weak base. Okay, acetate doesn't give off hydroxides, or I'm sorry, doesn't give off hydrogens. Acetate is going to take in hydrogens, right? It is an acceptor of hydrogens, not a donor. So this is a very weak base. Now, since we've switched into base mode, okay, now I'm operating with a base. Instead of using my Ka value, I'm going to work this from a Kb perspective. Okay? Now, why? Again, because this is the mental leap here that's tough. Because now I'm out of acid. The acid, I'm not going to have any free H plus at any point really from here on out. Okay? It's all being consumed up. I'm going to have more on the OH end. Okay? So essentially this is also the point where we're going to start to be in a basic situation. Okay? Now, this is important. Essentially, anytime you're titrating a weak acid, it's going to be basic at the equivalence point. Okay, and that's a sort of a fundamental thing that you need to know that will help you out on the AP test. So, how do we calculate our Kb then? Well, we're going to use our Kw value like we've been using all year. That's going to tell me that my Kb value is 5.6 times 10 to the negative 10th, and that's going to give me a new equilibrium equation. Now, what you'll notice here is that this equilibrium equation is essentially this equation in reverse, right? So if instead of starting at instead of starting this way and running this way, if I ran from acetate back this way, that's this equation. Now, why am I doing that? Again, I'm at the basic point of my titration. I'm out of acid. Okay, it's been fully consumed, and so now what I have left is a base, and that base then is going to basically every time is going to react with water, and it's going to produce these two things. Okay, so that sort of changes up the dynamics of what we're doing here just a little bit. Okay, so now we've got a Kb value instead of a Ka value. So now let's calculate the pH here, because this is the equivalence point. This is kind of like, this is the important part of what we're doing here, right? So what do we do now? Well, we're going to do an ice table again, except this time, okay, we're in a basic solution, and so now I'm going to be using this. Now, does that really substantively change my ice table? Well, a little bit, because for this one time here, what we're going to do now is I'm going to use these things, okay, these particular ions in my ice table. Okay, so I've got the acetate, and then I've got the actual acetic acid, and I've got the OH minus. Now remember, if we plug in everything, I've got 0.005. Okay, whoops. Now, one thing that we forgot to do that we did in the last one is that we've got to convert these things back to molarity, right, before we can do the equilibrium part. So 50 milliliters plus 50 milliliters now means that I'm dividing by 0.1, right? And so now I'm going to get my molarity value of 0.05 instead of 0.005. Okay, so come over here to our ice table, and I've got 0.0, that's a 0, 50. I don't have any of these, right? 0. And so naturally, when the ice table looks like that, it's easy to tell we're going to lose that. We're going to gain these two. Okay, 0.050 minus x. And then we've got x and x. And of course, as we've done 100 times so far, I'm going to get rid of this x. I'm going to assume it away because it's relatively small compared to this number. Now, remember the cutoff point is 10 to the negative fourth, and that's a whole lot smaller than that. So x is going to be really, really small. And so that's an easy assumption to make and to assume away. So don't stress about that, although I know some of you probably will. So now we're going to plug that into our new law of mass action for our base. So 5.6 times 10 to the negative 10th. Okay, and that is equal to x squared over 0.05. Okay, and so now we're going to solve that for x, and x is going to turn out to be 5.3 times 10 to the negative 6th, somewhere around there. Now remember though, in this case though, x is not H plus, X is OH, okay? And so the easiest thing to do, I mean, we could convert that into H plus, but the easiest thing to do is to calculate your POH, okay, and then to subtract from 14, and once we do that, that is going to give us a pH of 8.72. Now remember we said just a couple of minutes ago, it's pretty much has to be basic. So now we're going to jump back, we're going to plug that one in, and then we'll try to run through the last couple of calculations. So now I'm at 50 milliliters, and I'm not at pH 7. Like sometimes that's what we think, oh, it's neutralized, it's at pH 7. No, I'm at 8.72, okay, so somewhere around there. And so now we can kind of draw the substantive part of our graph, right? Like this is what we were really worried about. That was a terrible. Okay, so now we've got sort of the meat of our titration. We know where the equivalence point is. We could pick an indicator, right, that would be somewhere on this vertical part of the graph. But now let's see where we finish up. So what's going to be the pH that we're going to end around? So let's jump over to those. What happens once we start to add more base, okay? Because this is where a little bit more thought comes in. This is where we're like, okay, what do we do now equilibrium-wise? Okay, so same equation. We're still in the basic side of things, so we would use this equilibrium equation if we were going to do equilibrium. And you're like, why are we not doing equilibrium? Okay, hold on a second. Let's go ahead and calculate what we know so far, and then we'll talk about what's different in this particular problem. So now I've got 0.006 of my hydroxide, 0.005 of my acetate, or acetic acid rather. I had none of my acetate to start with. So in this case, stuff is going to get consumed. The acetic acid is going to get completely consumed, and that means I'm going to have 0.001 of the OH left, and 0.005 of my acetate. Okay. Now here's where some thought comes in as far as the equilibrium part of things. So like part of our brain would think, well, I'm going to set up an ice table, and I'm going to do my concentrations of these two things, right? Because now I've got 110, so 0.110, right, and 0.110. And I'm going to calculate each of those. So let's go ahead and do that a little bit. Okay, so that's going to give me, I want to say 9 point something. Hold on. Let me look at my calculations. So that gives me 9.1 times 10 to the negative third. And we could calculate this part out, okay? And that is going to give us, okay, so that's going to give us 0.045045 of my acetate ion. So here's where the trickiness comes in, is that, you know, you're looking at this and you're saying, well, which is going to contribute more base? Because I'm on the basic side of the equation, right? And essentially I'm getting the hydroxide from two places. I'm getting it from the hydroxide that's left, that's its concentration. And then if we look back at the last equation, the last slide here, okay, that we did just before, we said, hey, we're going to break acetate down and it's going to form the hydroxide, right? But it's really not. I mean, it is, but it's such a small amount. I mean, how much hydroxide did we get out of a smaller concentration, or I'm sorry, the same concentration of our acetate last time? And actually, it's a lower concentration now because it's a greater volume. Okay, so how much hydroxide did that produce? Not really a whole lot, right? Okay, we got this much hydroxide times 10 to the negative sixth, and 5.3 times 10 to the negative sixth, and I've got 9.1 times 10 to the negative third here. So that means this is like 1,000 times more than I could possibly get out of this. And so what that means, okay, and you're not going to like this, but it makes the math easier. What that means is that this is insignificant as far as producing hydroxide ions compared to this. It's 1,000 times smaller. In other words, it's not even going to like make a dent in how much we have here. Now here's the good news though, is since I already know my hydroxide concentration here, now I can just plug that into POH, okay, and then I can find my pH because all of my significant hydroxide comes from here. And so when we plug that in, that's going to give us a POH of 2.04, which means that the pH is 11.2. 0.96. Now again, don't let that freak you out. It's just that this doesn't matter. If you wanted to plug it into an ICE table, you could, but you're still going to end up with this same answer here because this isn't going to really make any difference in the overall scheme of things because it's 1,000 times smaller. So now jump back to the graph, and we are at 60 milliliters now, and now my pH is really getting up there, right? So we're somewhere around probably up here at 60 milliliters, and so now you really can see the shape of the graph. This is the point where you could probably sort of let it go at this point. You might want to do one more point though, and that's what we're going to do. We're going to do one at 75 just to sort of see the overall shape of the graph. Okay. Now the 75 calculation is going to work exactly like the 60 did. We're going to do the same thing. This part, the acetate part, is going to be pretty insignificant compared to the actual hydroxide already being produced, and not being produced, being dropped in, right? That's the base that we're dropping in. So let's go ahead and work this one real quick. 0.0075, and I'm sorry for the length of these videos, guys. I'm trying to make sure that everything is as clear as possible to you. Okay, so that gets zeroed out. We're going to consume all of that, and that's going to leave us with 0.0025 of my hydroxide, and then obviously I would get 0.005 of my acetate, and then we're going to divide by our new volume, so 0.125. And again, I'll be honest, I'm not even going to do this calculation because it just doesn't matter. It didn't matter in the last problem, and it was really small in the 50 milliliters, so it's not going to matter at all compared to what the value of this particular calculation is. And so in this case, this is going to come out to be, whoops, sorry, lost my pen, 0.02. And again, that's my hydroxide concentration, right? So I can just plug that right into my POH, and we get a POH of 1.7. And so that means when we subtract that from 14, that we're going to get a pH of 12.3. And so now we jump back to our graph, and we say, okay, 75, I'm at about 12.3, which is a little bit higher, but not much. And so that means that I'm basically tapering off like this. Okay? So there are a couple of things here that as you're working through the whole problem that you want to make sure that you get. Okay? So when you're still in the acidic side here, when we're in the pre-50 milliliters, pre-equivalence point, then it's the Ka value that we're going to use to calculate things. Okay? Once we get to the equivalence point, everything starts to become basic, and so we're then going to start to use our Kb value, and we're going to do an ICE table with Kb. Once we got past that, since it was such an insignificant amount of hydroxide that's produced from our conjugate base here, from our acetate ion, we're not even going to worry about it. We're just going to take our OH that we actually get from the stoichiometry part, and then we're going to give it its new concentration, right? So we did the stoichiometry, we had this number of moles, divided it by its new concentration, and that then becomes the OH. Once we have OH, we can calculate POH, and we can calculate pH. Or, once you have OH, you can calculate H plus and then calculate pH directly, whichever way works for you. Alright guys, I'm sorry these videos together were so long, but I think that they're going to be really helpful to you as you're not only prepping for your test, but as you're prepping for the AP test as well.